Welcome back, everyone. I see there were already hands raised. Yes, please.
So, first question, when is the deadline for submitting the exercise sheets in general, and when is it particularly for the first one?
Good question. So in general, we decided to put this on Fridays. So you're not going to be tempted to work over the weekend. So it's going to be Friday, 6, 7 p.m. around that time. And the first exercise sheets will be due next week at that time. Friday at 6 p.m. The first submission is next Friday around 6 p.m. I don't know what the tutor, what the TAs decided specifically, but the internet is the entire building. So let me see if I have something to make the internet. One second. Verstanden. Oh, geez. Let's see. So I didn't bring a cable, but let's hope this remains somewhat stable. Okay, I'm gonna maybe I don't see the record button anymore. Oh, did that? Here. Okay, no, recording still in progress. Good. All right, so let's get started today. So first, a quick announcement. Also, let me take the time. All right, lost already 5 minutes. So the first exercise sheet will be released tomorrow, and please register a new team or join an existing team on CMS. So in case you haven't seen this yet, that there's this option Teams. Either create one or join one, then you will be able to submit exercise sheets as a team. So we had already one question in that regard. Are there further questions? If not, then let's continue. So the topic of today's lecture is going to be probability or probability theory, and my go-to book on this matter is the book Probability and Computing from Michael Mitzenmacher and Eli Upfal. This is really the best or most gentle introduction to comprehensive probability theory for computer scientists, right? Let me also rearrange the windows here. Good. Let's hope this remains stable. All right, this book should be in the so-called Semesterapparat. There's a link on the homepage. So if you're taking a liking in these topics we'll discuss today, this is your go-to book. All right, so a quick overview, what we're going to do today. First, I'm going to introduce probability spaces, events, and probabilities. Then we're going to talk about the very important notion of conditional probabilities, and therefore also the so-called Bayes rule, right, which is a very popular topic in popular science. And when we're talking Bayes rule, we'll also talk about the law of total probability. And finally, we're going to discuss random variables. Okay, so first off, why randomness and probability? So probability theory is a mathematical framework for systems which behave in unpredictable or random ways, right? Sometimes scientists, especially in, let's say, human sciences, use probability theory to model systems that are just too complex to model with, let's say, precise math, right? So what we're going to do is we're going to try to capture some aspect of such a system in a statistical or probabilistic way. So in most sciences, the systems that we look into or that we're interested in studying in, think about the voting behavior of a large population, right? Such systems are way too complex for exact modeling. And furthermore, we have a lack of precise measurements, right? In order to really precisely predict the outcome of an election, you would have to talk to every single voter beforehand to see how their sentiment is. Good. So in most sciences, we use probabilistic modeling because it's in some sense the best thing we can do. Computer science, on the other hand, we see, let's say, randomness or probabilism more as a resource, right? I don't know how many algorithms lectures or different algorithms lectures you've attended so far. But one thing that's sort of strikingly or comes as a surprise when you start studying is that randomness or probabilism actually seems to make algorithms stronger, right? There are, as a matter of fact, problems where we know efficient algorithms that use randomness, but without using randomness, no such algorithm is known. For a long time, the go-to example in computer science to demonstrate the power of randomness was primality testing, right? I'm going to give you a very huge number, and I'm going to ask you, is this number a prime number, right? Now, if you just stick with the definition of prime numbers, you would say, okay, good, there's an algorithm, just divided by all primes, divide this number by all primes that are smaller than square root of n, and if none of them divides n, then you can be sure that your number n is a prime number, right? But there are much better tests, and we're going to see them in this lecture, not in my part, in the second public key part, where you're going to give me a number and you basically just do a few so-called modular exponentiations. And if you do that like 5 or 6 times and you do a test after this exponentiation, and if your number survived this test, you're with 99.999999, make it any number of nines you want, percent certain that this number is a prime number, right? So for a long time, this was the go-to example until which year? So who in the audience is familiar with computational number theory? Until the year 2002, when the so-called when a paper appeared that's called primes is in P, or meaning there is an efficient deterministic algorithm which checks primality, the famous AKS02 result. I think Agrawal, Kaya, and Saxena. Good. There was a big surprise back then that testing primality is actually efficiently doable without the use of randomness, but this algorithm didn't have a practical impact. So still today, we are using probabilistic or randomized algorithms to check primality of primes. So when you generate, let's say, a new PGP or GPG key on your computer, the primality test that's going to be used there, if you use something like RSA, will be a randomized test, right? And not the efficient but not practically efficient AKS test. Okay, so in computer science, in general, we see randomness as a resource, right? It's not a bad thing for us. Like, we don't just use it to capture elements we cannot, or events that we cannot model more precisely. No, we really use it as a resource. And when it comes to cryptography, it's an indispensable resource. Cryptography, as we will see, is, as a matter of fact, impossible without randomness. If you don't have, let's say, some source or some generator of randomness, then cryptography will be impossible, right? Hence, the need for this lecture to discuss probability theory in a bit more detail. All right. But first, I mean, I've talked already a bit about the randomized primality testing algorithm, or the so-called Rabin-Miller test. I don't think we're gonna really do this algorithm later in all detail in this lecture, but let's quickly develop an intuition of how randomness can help us to develop efficient algorithms, right? Let's say, for instance, we're having elections, right? This was a few years back, like till in the German polls of the year 2021. And in Germany, you have roughly 40 million, 40 plus million voters. So let's say they're all good citizens and they all go to cast their vote, which they don't. But then to really know the election outcome precisely, you would have to count all the votes, right? But let's say people are anxious to get to know the results, who's going to be the new chancellor or whatnot. So what do you do? How do you estimate who the election winner is? So what's let's say I was to say, okay, good. So I know where my friends vote. They vote in let's say St. Johann, and I'm just going to go to St. Johann and ask the first 20 people what they voted for, and I'm going to use that to predict the election results. Is that a good approach or a good algorithm? Yeah. Come again, a bit louder.
It's not representative of the whole.
There you go. It's not representative of the entire population. So you're going to get a very what we call biased sample. So and one thing you can do to get a good estimate is to get a random or unbiased sample of, say, 10,000 votes, and you will be able to determine the outcome of the election. We could do the calculation, but until after the second position after the point, right? So here the important thing is to take a random sample of the entire population, and that, as a matter of fact, leads to a good algorithm to predict the election outcome, right? But for that, I need randomness. I need to choose these 10,000 people. I cannot just go to my neighborhood and ask 10 folks there, right? That would be the way to do it without randomness. Once I do have access to good randomness, right? And this is, as a matter of fact, getting good randomness is a non-trivial problem in computer science, as we're going to see. But once I have this randomness, I have a very robust algorithm to predict the election outcome. Okay, any questions? Any more questions regarding this? Okay, good. So then let's get a little bit formal. By the way, is someone, oh, there's a question in the chat. Well, can you repeat the question from the student? I cannot hear their voice. Thanks a lot. Yes, I'm going to try to do that. I think I did it with the last question. But all right, good. So how are we going to model randomness? We're going to use so-called probability spaces. So let's first introduce what a probability space is. Probability space, I'm gonna rest my palm here, so zip, zip. A probability space consists of a finite set. We call this omega, and when I'm gonna do black, when I'm gonna do draw. Oof, what is happening now? Yeah, interesting. He doesn't recognize my pencil. Ah, now he does. Good. I'm gonna draw this as such a box. So just to symbolize our probability space, that's gonna be the frame in which we're gonna move around. And the second part is the second component of a finite probability space is a probability function, right? We call this, we typically denote this with PR, which takes an element from this sample space, let's call this little omega, and maps it to a real number between 0 and 1, right? So if you give me an so-called elementary event omega, whoops. If you give me such an omega, which we call elementary events, then our probability function will map it to a number between 0 and 1. And we have the following additional constraint or the following normalization. We require that if we take the sum of all PR omegas, of all omegas in this probability space, then we sum up to 1, right? Meaning, now comes already an interpretation, we interpret probability omega as the probability or the chance of this elementary event omega. Let's try if we get a better connection with this cable here. Oh, this cable seems to be broken. So there's, I don't think that's going to lead to a. Was there a question? So. I think I'm going to have to restart the screen sharing. Oh, so I was. Yeah. Oh, Jesus. Okay. Now it seems that we're having trouble. Oh, wow, that's a lot of cable. Thanks. Okay, good. Okay, das ist kleine Reihe. Let's see if we're having a proper connection. Should be this one here. So it seems like I'm now we should be connected. Oh my, sorry everyone. Okay, good. Let's hope this remains somewhat stable. I probably will have to. Okay, the recording is still in progress. I think we just lost 10 minutes. All right. So again, we have this probability function which assigns a chance, likelihood, or just probability to these events. And now if you give me a set, let's use a different color, a set E in omega, we call this an event. And for such an event E, we naturally define the probability of this event. By the way, you're going to tell me if something goes wrong with the beamer or not, so I don't need to constantly check. For such an event E, we naturally define the probability of E as the sum of the probabilities of all elementary events omega in this event E. Good. And yeah, and now that was too fast. We might have, of course, also the empty event, right? Which is essentially nothing happening, which corresponds to the empty set, and we just define the probability of empty set or empty event as 0. Okay, good. You can think of this as probability of false. Yes, please. Yes, that's a finite probability space. So for this lecture, it's going to be enough to talk about finite probability spaces. So of course, the math is much more beautiful, and mathematicians have consider continuous probability spaces to model more complex systems. But mostly in computer science, mostly, not always, sometimes continuous modeling helps, but mostly in computer science, we stick with discrete probability spaces or finite probability spaces. So discrete and finite are not the same thing, right? For us, we just need finite probability spaces. So where this probability space omega is a finite set, right? I wrote a finite set. In discrete probability spaces, this set omega is a countable set, right? You have a onto or surjective mapping into this set from the integers, and a continuous probability space might be uncountable, right? So as having the same cardinality as the real numbers, if you want so. Okay, thanks for the question. And please keep the questions coming. All right, examples. Here. So the cryptographer's favorite example is the fair coin toss. There, our probability space just consists of 2 elements, and we call them 0 and 1. And we just say probability of 0 is the same as probability 1, which is 1/2, right? What we model with this is when we toss a coin, then both the probability of 0 or the outcome 0 and the outcome 1 have the same probability. That's why we call this a fair coin toss. Okay. That's the first example. The second example is a so-called biased coin toss. So give me any real number p between 0 and 1 and a p-biased coin, as we call it. Here we have probability of 1 is p, I think maybe 1/3, and probability of 0 then has to be 1 minus p, because these two probabilities have to sum up to 1. Now a next example is a fair dice roll. Here our probability space consists of the numbers 1 to 6. This is just the outcomes of a dice roll, right? And we ask that the probabilities of all outcomes, since it's supposed to be fair, are exactly 1/6. And of course, this generalizes to the notion of uniform randomness over a finite set, where our probability space consists of numbers 1 to n, and each outcome should have the same probability, namely 1/n. Zip. Oh, there's again questions. The tablet is not in the Zoom meeting. This was earlier. Okay, good. The tablet should be here. But yeah, next time I'll probably gonna bring a bunch of cables to make sure that we have a slightly more stable connection in here. Was not an issue with the last years, because in my office I do have a proper internet connection. All right, but now we define events as sets. And the next thing we can do is, of course, define. Again, tells me my internet connection is unstable. Let's hope it remains stable. Or it becomes stable again. Let's take our probability space omega again, and let's take events E1. And another event, let's call this E2. Then the intersection of these two sets, it's again a subset of omega, of course. And we call, this is now E1 intersect E2. Of two events, E1 and E2, we interpret this as the logical and of these two events, right? When we're in the intersection of event E1 and E2, then we think of this event as both E1 and E2 coming true, right? And we just introduce the following notation. So for this intersection, E1 intersect E2, we sometimes just write probability of E1 comma E2. So sometimes this is really just notation, right? When we introduce a comma in the probability, or we write this logical and operator, this wedge operator, or we just write out and, right? Those are all different notations for the same thing, and depending on the author, maybe the mood of the author who's currently writing that, but all meaning the same thing, but people use different notations. So the union of two events, right? I'm tracing the line here. This is E1 union E2. This is interpreted as the logical OR of these two events, right? And we will write, I mean, here we have less options, probability E1 union E2 or E1 OR E2 as E1 VE2 or E1 OR E2, just written out. Okay, good. So much for this, but there's more set operations to come. Let's again write our omega here. And again, let's take let's use green. Let's take our set E here, right? Then the complement, right? E bar, let's use a different color. E bar is now just omega set minus E, right? This is E bar is just everything outside the event E, and we associate this set complement with the logical negation or logical not, right? And we write probability E bar as probability negation of E or probability not E, right? So far this is all really just notation. And finally, if again we have an event, let's say A, and this set that defines this element A is contained in another event or set B, then we say that the event A implies the event B, right? Meaning that whenever an elementary event in A comes true, then we also know that this elementary event or elementary outcome is also in B, right? So if event A happens, then event B also happens. But again, this is for now just notation. I see there's no more questions here. All right. Any questions so far? Okay, good. Then let's start to make things more interesting and look at a few properties of probability spaces, right? The first one will be, well, for all events A and B in probability space omega, it holds probability A or B is the same as probability A plus probability B minus probability A intersect B. Okay, probability of, and here, let me finish reading this. Probability of A complement is just probability or 1 minus probability of A. And probability, sorry, if A is included in B, or if the event A implies B, then the probability of A is smaller or equal the probability of B, right? So mathematicians typically refer to probability spaces as measure spaces, right? Because that's precisely what this probability function in the end, from a mathematical perspective, does. It measures the size of a set, right? A set being an event, and I mean, we have these natural things here. For instance, zip, zip, zip. Let's look into just very quickly into the first item, right? Why is probability probability A union B the same as probability A plus probability B plus minus probability A intersect B? Well, if we look at this, probability A union B is just summing up the probability, all the probabilities in here. Okay, but if we were first to sum up all the probabilities in the green area and then add to that all the probabilities in the red area, then of course we would be double counting what's in the intersection, right? That stuff would be counted twice. So that's what we have to subtract to arrive at this conclusion. And the same is if we, for instance, look at the second item, right? We know that A union the negation of A. Negation of A, this is the entire probability space, right? But now we know that, well, the entire probability space has probability 1, right? So this is probability A union A bar, or negation of A. But by the first item, we know, well, a probability of a union of two events is just a probability of A plus probability of A bar minus probability A intersect A bar, right? But now we've seen on the previous slide that well, the two sets A and, there should be a bar here, A and A bar, they are disjoint, right? The intersection is the empty set. Whoops. So this A intersect A bar is the, this is the empty set, and therefore this probability here is 0, right? Probability of the empty set is 0. So now we have 1 equals probability A plus probability A bar. So if we rearrange this, we have that probability of A bar is just 1 minus probability of A. Good. Any questions regarding this? And now, of course, if we go to the third item, right? If A is included in B, then probability A is smaller equals probability B. I think you can do that yourself. Basically, what you're doing, you again write out the probability of B as a sum over all elementary events in B, right? And now you just have to drop a few elements or a few elementary events. Namely, those are not in A, but you know that for each of those, the probability is going to be greater than 0. So if you drop those, you're only making the probability smaller. Okay, so this is a very simple thing, but also item 1 from above implies the so-called union bound, which is a let's say probability theoretic tool we're going to make excessive use of. Right, this is something very simple, since we know that a probability A and B is greater equals 0. That means minus probability A and B is smaller equals 0. Right, from this it follows that probability A or B is smaller equal than probability A plus probability B. Okay, this is a very simple thing, and see if that's on the next slide. And of course, this immediately generalizes to if you have probabilities of A1 or A2 or and so forth, or AN, this is smaller than the sums of the individual probabilities. Okay, this is a direct inductive conclusion of this union bound for two sets or two events. It also holds for any number of events that you might want to look into. Okay. All right, good. So far the simple things, and now let's introduce a slightly an additional concept to this, namely the notion of conditional probabilities. So first, what's the definition? I'm first going to give you a definition, how conditional probability is defined, and then I'm going to give you the intuition. So the definition is, if you have two events A and B, and I constantly, I should have fixed this, we have to ask that the event B is non-empty, right? Because you're going to see we're going to divide by probability B, and that shouldn't be 0. So for two events A and B, we define the conditional probability of event A given event B, right? We assume that event B has happened. Now we're asking, given that we know that this happened, what is the probability of event A happening, right? And this is defined as probability A intersect B divided by probability B. Let's maybe start with a very simple example, right? From earlier, let's say we have our event B here, and let's say the event A is yes, the event sorry, now I did it the wrong way around. Let's change things. Let's make the outer one the event A and the inner one the event B. So let's say B is contained in A. Now, what is probability of A given B? Can anyone tell me? Yes? Why?
Because, I mean, if you take intersection, you will end up with B, and then you have the probability of B divided by B, and it's 1. Good.
So conditional, if the event B sort of implies event A, then of course the intuition is then, or the interpretation of this is, right? We know that A happened for, if event B happened, then A happened for certain. So the conditional probability should be 1. Okay, but now let's make this more interesting. In general, right, we have, let's say the green one is now an event B, and let's say event A is this, and this is A intersect B, right? A intersect B. So the interpretation of a conditional probability is really just that of renormalization, right? Instead of, so we're starting off with a probability space omega, and if we condition to an event B, then our new probability space will just be the set B, right? So in the end, conditional probabilities are just a simple renormalization of the probability space. So before the probability space was this black box, or the outer box omega. And when we look into conditional probabilities, the new probability space is the set B we've conditioned on, right? So therefore, in the definition, all we do is a renormalization, namely by dividing the probability of this event A intersect B, and anything that's outside of B doesn't interest us anymore by the probability of B, right? So when we're talking about conditional probabilities, really think of shrinking this probability space to B, and thereby renormalizing our probability function. Any questions? Maybe any questions online? Anything still, yeah, still working? Okay, good. But let's go a step further. We say two events A and B are independent, or we define A and B to be independent if it holds that probability A intersect B equals probability A times probability B. Sounds like a weird thing at first, right? Most people who take these, who see this at first think, hey, shouldn't two events be independent if, let's say, probability A, here you have a set A and B, if A and B are disjoint, right? If shouldn't that be independence? But it turns out that this having disjoint events, which basically means those two are mutually exclusive, right, is something else than being independent, right? Namely, the sort of so this is wrong, right? This is not independent, or can I reverse this somehow? Nah, no, I can't. This is disjointness, or mutual exclusivity. So you're getting the right intuition for independent probabilities if you resort to the conditional probability, right? Let's say we have independent A and B, and now probability A condition B is just probability A intersect B divided by probability B, right? But if A and B are independent, here A comma B independent, this is just probability A times probability B divided by probability B, right? Which is just probability A. So, and now we get the proper intuition what it means for two events to be independent. Whether event B happened or not doesn't bother my event A, because it stays invariant, even if we condition on the event B happening. The conditional probability of A condition B is still the same as probability of A in the entire probability space, right? This is what it means to be independent. A doesn't care whether B happened or let's say or not happened. And of course, the same is true with probability B condition A is now also probability B, right? This is what it means to be independent. For two events, they don't they are sort of in a position where they don't care if the other one happened or not. Their probabilities or conditional probabilities don't change, right? This is a very important concept, because once we realize that let's say two events are independent, our calculations are most of the times going to be much simpler. Good. Okay, so this is, I mean, okay, good. What I just wrote is already there. Let's say, okay, but let's look at an example here. namely fair dice rolls. And here I have to write this. And by the way, it's I'm already over time. Let's make our 5-minute breaks. Sorry, I overslept the 5-minute break because of all the outages in the internet. Let's come back together at 1:30 and please remind me if I forget about the break. Turn on the speakers here again. All right. Good. Let's continue. Now, example dice rolls. So I've said earlier that for a single dice roll, our probability space is just the set of elementary outcomes being numbers 1 to 6. And since it's a fair, let's say it's a fair dice roll, the probability of each elementary event here is 1/6, right? But what if we have 2 dice rolls? Well, let's call this omega-1, then omega-2. Let's make this simple. There's, of course, you have some degrees of freedom in modeling this, but let's just say it's pairs of outcomes, ordered pairs of outcomes, namely outcome of the first dice roll, comma, outcome of the second dice roll, right? So it's 1-1, 1-2, whoops, 1-3, and so forth until if we go through all of them, 6, 6. Right, and now the elementary events are these pairs ij, and if it's 2 independent and fair dice rolls, then the probability of each elementary event here is 1/36. Okay, so now working with this probability space, what is probability, let's say first dice roll is 1. What's that? We roll twice, and what's the probability? 1/6, exactly. 1/6. Good. But now let's ask, what's the probability of second dice roll? Dice roll is 2, given first dice roll is 1. What's that? Yes? Any differing opinions? 1/6, yes? 1/6. Let's just do the math, shall we? So we have probability. If we define this as, how do we call this? E2, and this is E1, then this is probability E1 intersect E2 divided by all right. Everyone online, I've decided to call an end for the lecture today. Next time there's going to be actual Ethernet cables to connect us to connect my computers. Sorry for the inconvenience today, and see you next time. Thanks, everyone.